Hello everyone. Let's have a look at an example related with design of a condenser. So here, for example, we have a condenser that there are 2500 thin wall tubes in that condenser. We know the thermal conductivity of the metal. We know what is the outer diameter of the tubes, and we also know that these tubes are arranged in a square array. And as such, we can calculate how many tubes are present in a vertical row. Okay, so for example, if you have 2500 tubes, and if you want to arrange these 2500 tubes in a square bundle, so you need to have 50 by 50 tubes, okay, to get a square. So it means that if you count vertically, we can get 50 tubes, and these 50 tubes, you will see later why we need that, why we need this number. Okay, and we also know that the condensation is happening in the shell because the tubes are exposed to the condensing fluid, that is steam. And so we have to calculate what is the mass of the steam condensed per unit length of the tube, because we don't know what is the length of the tube. And we know that the wall temperature of the tube is 98 degrees centigrade. We also need to calculate what is the overall heat transfer coefficient, given that there is no fouling inside and outside the tube, and we know the heat transfer coefficient of the tube. Okay, so we know the value of HI. Okay, and we need to calculate U C, because there is no fouling, so we have to calculate clean overall heat transfer coefficient, but we don't know what is the value of H naught. Okay, or in this case we can call it HC. Similarly, we also need to calculate what is the value of Q based on this condensation. Okay, so let's look at the solution of this problem. So first we have to decide what is the saturation temperature of the system and what is the tube temperature. So we know that the tube temperature is 98 degrees centigrade because it is given in the question. And we know that the saturation temperature of steam is 100 degrees centigrade. So both these values are known to us. Okay. So what is happening? So we have these arrays of tubes, and the condensation is happening at the surface of the tube. And similarly here, so if we assume that you are having film-wise condensation, that is normally the case, so we can actually use the Nusselt equation to calculate HC. Okay, and also we know the temperature at the tube wall, that is 98 degrees centigrade, and the steam is here in the shell. Okay, so the temperature of this shell or the steam is actually T saturation, that is 100 degrees centigrade. Okay, so because in the question we are not given any properties, and it means that we have to look those properties in the steam table. So once you know these two temperatures, you can calculate the midpoint temperature, that in this case would be 99 degrees centigrade. And then based on that, we can calculate the physical properties of our system. Okay. And then we need to calculate the thermophysical properties, and these thermophysical properties are for the case of vapor, that is steam. So we know that at atmospheric steam temperature of 100 degrees centigrade, the density is this and the heat of condensation is this. So please remember that when you are talking about normal properties, you are talking about using a midpoint temperature, but when you are looking at the properties of the steam or the condensing fluid, you are going to use T saturation and not the midpoint temperature. Okay, because these systems are at 100 degrees centigrade, not at 99 degrees centigrade. Okay. Similarly, when you do these kind of calculations for boiling, please remember that for the case of liquid properties, you will use the boiling temperature, but for other properties like viscosity and density of the vapor phase, you will use an average temperature. Okay, so we know these properties. Now we need to calculate what is HC. Okay, so how we can calculate HC? As I said before, that we can use the Nusselt equation like we discussed in our lecture, and Nusselt equation for one tube can be given here. Okay, so we have a range of properties. We know the diameter of the tube, we know the delta T of the system. So we can also simplify this equation by ignoring rho v, because if you see from the previous slide, rho v is 0.98 compared to 960 for the liquid. Okay, so you can ignore it. But if you use this whole equation, it is not going to make a difference. So that's why I just make it simplified. And this equation is based for one tube, but because we have 2500 tubes, it means that we are going to have for example, condensation, and then it is going to drip from the top tube to the bottom tube. So we need to have a correction factor as well. So if you remember from the lecture, we use this correction factor, the empirical correction factor of number of tubes in a vertical array. Okay, and by using this, we can actually correct this equation. And now we know the values of all these properties, so we just have to add into equation. And as I said in the beginning of the question, that NR, we can use 50, because if you have a 2500 tubes in a square array and you have to arrange them in 50 by 50, so if you count the number of vertical tubes in this tube bundle, you should get 50 tubes. Okay, so we know all the properties, and if you feed the value, we get HC, that is related to condensation at the outside of the tube, so we can call it also H naught. Okay, so we know the value of Hc. Now we can calculate what is the total surface area of the system per unit length. So we can write it as A is equal to pi d ln, and because we don't know L, so we brought it in the denominator here. We know the value of d naught, so that is the outer diameter. We know N, that is 2500. So this is the total surface area of heat transfer. Okay, for heat transfer, the area that we required. So that is 98.1 meter. So this is not meter square, because we are calculating area per unit length here. And if we know the area, we have this equation, that is the heat transfer, universal heat transfer equation, where Q is equal to Hc, the film transfer coefficient due to condensation, times area of heat transfer times delta T. We know the value of all these parameters, so we can feed it into the equation, and we get the heat that the condensing steam is going to release, and that will be the total heat, because it is based on 2500 number of tubes. Okay, so that is one part of the question that was pretty straightforward. The only thing that you had to do was to select a correlation, and in this case we use Nusselt correlation, but you can use any relevant correlation depending on if the equation that you selected is within the limit of the system. Okay, so you have to check all the Reynolds number, all the properties, and the limits of the equation that you are using. Now, in the second part of the question, we are supposed to calculate the overall heat transfer coefficient, and in this case, because there is no fouling, so we will be calculating the clean overall heat transfer coefficient based on one tube. And if you write the formulation, or if you simplify the long formulation that we saw in previous lectures, for no fouling case, we come to this relation here. And then we know that Hi is the tube side heat transfer coefficient, and we have the value given in the question. For the HO, that is the outside heat transfer coefficient, we calculated it by using the heat transfer coefficient for condensation. Okay. In the previous part, we calculated the heat transfer coefficient for the whole tube bundle, but because we are calculating UC based on one tube, so we have to convert this HC for the whole bundle also to one tube based calculation. So here it means that we have to divide the overall heat transfer coefficient with this correction factor, and if you do that, we get the final value of HC given here. Okay, and if you now feed the value of HI that is given to you in the question and the value of H node for one tube that we calculated here, we can get the final value of UC or U node, that is the overall heat transfer coefficient based on the outer area of the tube. Okay, so that is all for this part. Thank you for your time.